Hi everyone. So today we are looking at section 4.3. So last time we had talked about the addition rules. As you can see today we are going to be talking about multiplication rules and of course conditional probability as well. So when we're talking about multiplication rules, we're basically talking about we can use this when again you're trying to find the probability of two or more events, which was kind of the same thing we did with addition rule, but the difference here is when we're talking about finding the probability of two or more events, we are saying basically those events are going to occur in a sequence, which means one after the other. So as you can see in our example here, we're talking about, okay, let's say if we toss a coin and roll a die, right? So those are the two events we're looking at. So we're basically saying we can find the probability of getting a head on the coin and getting a 4 on the die. Now these two events are what we would classify as independent events, because basically the idea is the outcome of the first event will not affect the outcome of the second effect. So basically we call them independent because, like I said, the outcome of the first does not affect the outcome of the second. So your two events, A and B, are independent if A occurs, does not affect the probability of B occurring, okay? So just some examples for independent events. You can roll a die and get a 6, which is one event, and then you can roll a second die and get a 3 on that. So rolling the first die and getting a 6 has no effect on, of course, when you roll the second die and get a 3. Same thing if you were drawing a card from your deck of cards and you get a queen on the first event, and then you put it back in. So that's what we're saying. We're replacing it. We're putting the card back into our deck, and then we are drawing a second card, and you in fact end up getting a queen again. So pulling that first card and getting a queen, replacing it, which is going to be the important thing here. You do have to replace it, put it back into your deck of cards, drawing a second card and getting another queen. So these would be considered as independent events. So if you have two independent events that occur in sequence, then the probability for them is basically going to be you find the probability of each event and you end up multiplying both the answers. So find the probability of each event separately and then multiply your answer. So as long as your two events are independent, then this is going to be your probability rule. So probability of A and B is going to be probability of A multiplied by probability of B, okay? All right, so let's look at our first example here. Here we're talking about, again, flipping a coin and rolling a die, right? So two events. So they want to know what is the probability of getting a head from flipping our coin and what is the probability of getting a 4 when we roll the die. So when you're talking about flipping a coin, remember you only have two events that can happen. You either get a head or a tail, right? And then the sample space for the die would be you get anywhere from number 1, 2, 3, 4, 5, or 6. So if you're talking about getting the probability of a head, well, that's one outcome out of 2 in your sample space. So that's the probability of 1 over 2. If we're talking about the probability of getting a 4, so that's going to be the number 4 out of 6 possible choices. So that's going to be 1 out of 6. And then if you just multiply, 1 times 1 gives us 1 on the numerator. 2 times 6 gives us 12 on the denominator. So that's a probability of 1 out of 12, or approximately 0.083 for the probability of getting a head and getting a 4. Okay? So here, they're actually just laying out all the different possibilities for our options here. So we're talking about if you got a head, then you can get 1 on your die, a head or a 2, head or a 3, head or a 4, head or a 5, head or a 6, right? And then the same thing with tail. So you can have tail and 1, tail and the number 2, all the way up to tail and a number 6. And you know, to get this sample space, you can basically think about where flipping a coin first. And you know what, let me show you over here. So this is for example 1 in our handout. So if we're talking about flipping a coin, so you can either get a head or a tail, right? And then after we flip our coin, we are going to be rolling our die. So you would get 6 events out of that. So this is where you would have either the number 1, 2, 3, 4, 5, and 6. And same thing if you got a tail first. 1, 2, 3, 4, 5, and 6, right? So if you list all of these outcomes, you would have heads and 1. So that's looking at starting here, and this guy here, head and 1, heads and 2, of course, and then you can list all the options. So those would be going through all of these numbers here with your head. So now that we have completed all of these options, we move down to tails, and then that would be tails and 1, tails and 2, and then of course you would go all the way down to tails and 6, which would then include all of these options. So you can see that's going to be a total of 12 outcomes, right? And if you have 12 outcomes, then our question was, what is the probability of getting a head and a 4 in this example 1, right? So that's the probability of getting a head and a 4, which is 1 out of a total of 12 outcomes, right? So that's the probability of getting a head, and the number 4 comes out to be 1 out of 12. So that's kind of what they're talking about here in this example 1, okay? All right, guys, our second example here is looking at cards. So we are saying a card is drawn from a deck, but here's the key word, it's being replaced. So we draw the card, see what card we have, and we put it back in, and then you draw your second card, okay? If we don't replace the card back in the deck, you do not have independent events. So just keep that in mind. So our probability here is talking about getting a king and a 7, right? So just think about the probability of a king. There are 4 king cards in our deck, right? So that's going to be 4 out of 52 here. And the probability of getting a 7, again, is there are 4 of the 7 cards in our deck. So that's also going to be a 4 out of 52. So the probability of getting a king and a 7 is going to be 4 out of 52 multiplied with 4 out of 52, which of course comes out to be 16 over 2007/04, or if you reduce that, 1 over 169, and that's a probability of 0.006. So again, you can see it's a pretty straightforward formula when you're trying to find these probabilities for events that happen in a sequence, and of course they have to be independent events, right? Alrighty. So how about we look at example 3 over here. Now this one is talking about selecting a colored ball. So you've got an urn which contains 2 red balls, 5 blue, and 3 white, okay? So they are saying if a ball is selected and its color is noted, kind of like we did with the cards, we take the ball out, look at its color, make sure you write that down, and then you're going to replace it back into this urn or this container, basically. So you're replacing it, then you pick a second ball, again, note down what color it is, and now you're trying to find the probability of these events. So you can basically keep repeating that, right? Take one ball out, note down what color it has, put it back in, take a second ball out, note down its color, put it back in, and so on and so forth. So the first one is asking us, what's the probability that we select 3 blue balls? So you have to look at each ball being one event, right? Which means we are selecting 3 blue balls. So you're looking at what's the probability of getting blue balls. So remember, in our first statement, they're telling us we have a total of 5 blue balls. And then if you add, and let me write that here, if you add 2 red balls, 5 blue balls, and 3 white, of course that comes out to be a total of 10 balls in the urn, right? So that's where we're getting this denominator of 10 here. And we've got 5 blue, so that's 5 out of 10. 5 out of 10 for our second event, and 5 out of 10 for our third event, right? Because we're wanting to know what's the probability of selecting 3 blue balls. So multiply all 3 of those probabilities together, you get 125 over 1,000, or you can reduce it as 1/8, which is 0.125 as our probability, okay? So again, remember the key thing here is once we take a ball out and note its color, we put it back in to our urn, and that's what makes these independent events, okay? All right, guys, so our second one was talking about what is the probability of selecting 1 white ball and then 1 red ball, okay? So this is going to be the probability of white multiplied with the probability of red. So remember, there are 3 white balls, so that's 3 out of 10, and there are 2 red balls, so that's 2 out of 10. Multiply those together, you get 6 over 100, or of course 3 over 50, which as a decimal is going to be 0.06. Okay, it's not too bad. Example C is also talking about a similar thing. So you've got 2 blue balls and the probability of selecting 1 white. So 2 blue balls, so that would be 1 event each for each of those balls. And then for the 1 white, so again, guys, we have 5 blue out of a total of 10. So that's 5 over 10 multiplied by 5 over 10. And then there are 3 white balls, so that's 3 out of 10, which of course multiplies to give us 75 over 1,000. Reduce that to 3 over 40, or as a decimal, 0.075. Okay? So you can take this idea and you can extend it to as many events as you like. So you can have 3, or you can have more than 3, as long as they're independent events. You basically just keep multiplying each of the individual probabilities, and then you will get the probabilities for all of those events as a sequence. So they're basically saying when a small sample is selected from a large population and the subjects are not replaced, then the probability of the event occurring changes so slightly that for the most part it is considered to remain the same. So they're basically saying if you take a small sample from a very large population and let's say you don't replace your subjects, they're saying the probability of the event occurring will have such a small change that for the most part your probability will actually stay the same as though you had replaced your subject. So that's basically what they're talking about here, okay? Alrighty, so let's go ahead and take a look at our next example here. This one is talking about bank robberies. So we're saying it was found that 3 out of every 4 people, okay? So 3 out of every 4 people who commit a bank robbery are apprehended, right? They are caught. So if 3 bank robberies are selected at random, they want to know what's the probability that all 3 of these robbers were apprehended, right? So they're saying let R represent the probability of a bank robber being apprehended. So since we're talking about selecting 3 bank robberies at random and then finding the probability that all 3 robbers were caught, that's going to be 3 independent events. So you're looking at probability of R being multiplied with probability of R times probability of R, right? And then in that very first sentence, they told us that 3 out of every 4 people who committed bank robbery were caught, right? So that's your probability. So that's going to be the chances of 3 out of 4 for the first bank robbery, or for catching that first bank robber, 3 out of 4 for the second one, and 3 out of 4 for the third one. So you're multiplying each of these, and remember, these are independent events, right? Because each of those robberies are selected at random. So the chances that they would be connected to each other, or rather one probability or one outcome would affect the second or the third outcome, is going to be independent, because one outcome is not going to have any effect on the second one. So these are all independent. So you just multiply 3/4, 3/4, and 3/4, which will give you 27/64, or as a decimal, 0.422. So that's approximately 42% chance that all 3 robbers were apprehended. So obviously you can see that's below 50%. So we would say it's more on the unlikely side that the bank robbers would be apprehended. So not very good chances, as you can see here. Okay. Alrighty. So our next example is looking at male color blindness. So we are saying approximately 9% of men have a type of color blindness that prevents them from distinguishing between red and green. Okay, so that's our probability right there. 9% of men have a color blindness which prevents them from seeing red or green. So if we're selecting 3 men at random, what's the probability that all of them will have this type of red-green color blindness? Okay, so again, these will be independent events, because selecting one person with comparison to the other will have no effect on the outcome, right? So we're looking at probability of the red and green color blindness. You're taking probability of C, and they're telling you let C denote the red-green color blindness. And then you're multiplying this for all the 3 men we selected at random. So remember, that's a 9% probability. So 9%, you are going to write it as a decimal, 0.09. So that's your 0.09 being multiplied 3 times, which will of course end up becoming 0.000729. And then remember, for your rounding rules, for decimals, for probability, is you always round to the first non-zero number after the decimal point. So that's why we're rounding it to 0.0007. So if you convert that to a percent, it actually comes out to be a very small number, because it's only 0.07%. So basically we are saying out of 100 men, 0.07 number of men would actually show this type of red-green color blindness. So we are actually saying there's a very minuscule chance that a man would have this kind of color blindness. So just kind of something to think about. So just as a fun fact, when I was living in Kentucky, I used to listen to this local talk radio show, and this guy, I think his name was Ryan, if I remember correctly, he actually had this red-green type of color blindness. So a lot of times his co-host would make a lot of fun of him for not being able to see some of these colors. And this was all in fun. He didn't mind that. He himself used to joke about it, but he's the only person I have known to ever have this kind of red and green color blindness. So just a little fun fact for you guys. Okay? Alrighty, folks. So let's go ahead and see. This was all independent events. Now let's talk about what happens when they are not independent. In other words, when they are dependent, right? So they're saying in all 5 examples, our events were independent of one another. But on the other hand, when the occurrence of the first event changes the probability of the second event. So if the first event changes the probability of the second event, then we would say that the 2 events are dependent, because if the first event happens and Like you can see here in this example, like the first event is we are drawing a card from the deck, but here's what's happening. We are not replacing this card that you just drew. We're not replacing it. We're not putting it back into the card. And without putting it back into the deck, we draw a second card. That first event is going to end up changing the probability of the second event. So they want to know what is the probability of selecting an ace on the first card. We did not replace it, and then we select a king on the second card. So as you can see in the next sentence, they are saying before an answer to the question can be given, we should realize that these events are dependent. So since we're selecting ace on the first draw, so for the ace, of course, you've got 4 aces in a deck of cards, so that would be 4 out of 52. But since we are not replacing that card, that means when we select the king for our second card, right? That's actually now going to be only 4 kings. We still have 4 kings in the deck, but now we don't have a full deck, right? Because instead of having 52 cards, we're only going to have 51 because this first card that I drew, I did not put it back in, right? So now that means the deck I have is only going to have 51 cards. So this is how dependent events will happen, where the first probability will end up affecting the occurrence of the second probability. And then, of course, when you multiply these, your answer is going to come out to be a little bit different than if they were independent events, okay? So just our little definition here, we're saying when the outcome or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed, we say that the events are dependent events. So just some examples for us to look at. They are saying if we're drawing a card from a deck, not replacing it, and then drawing a second card, which was the example we just looked at with our ace and king, this is going to be a dependent event. Selecting a ball from an urn, same thing, not replacing it, and then selecting a second ball will again be a dependent event. They are saying being a lifeguard and getting a suntan. Now this is an interesting event, right? Because think about it. If you are a lifeguard, be it at a pool, be it on the beach, the idea is, for most parts, these things are outdoors, right? Especially the pools. Beaches, of course, outdoors. So it's a part of the job, right? They are going to get a suntan. Unless you're lucky enough to be a lifeguard who is at an indoor pool, then yeah, maybe you may not get. But usually this would be considered as dependent events, right? Having high grades and getting a scholarship. So again, we know usually if you have really good grades, maybe when you're graduating from your high school and moving on to a college or something like that, if you have really good grades, really high grades, then the chances of getting a scholarship, of course, becomes really good for those students. So you can say these are dependent events. This one here is talking about parking in a no parking zone and end up getting a parking ticket, right? So that one time when you are maybe in a rush or you need to get somewhere and you're like, oh, I'm just going to be gone for 2 minutes, you end up parking in a no parking zone. More than likely, it's going to be one of those days where you end up getting a parking ticket, right? So parking where you're not supposed to park will, of course, be leading to getting a parking ticket. So again, those would be dependent events, okay? So just something to kind of think about when you're going through your homework and your examples for these. Okay, so they are saying there's going to be a modification when you're trying to find the probabilities for dependent events. So they're going to say use the multiplication rule with the modification in, with the modification in notation. So they're saying for the problem we just discussed, which was getting the ace on the first draw, not replacing it, and then getting a king on the second draw, right? So for the ace, our probability was 4 out of 52. For the king, it was 4 out of 51. So by multiplication rule, you would take the probability of each event, multiply them together, you get 16 over 2,652, which reduces down to 4 over 663, and of course that probability comes out to be 0.006. So they're saying the event of getting a king on the second draw when the first ace was drawn is what we call as conditional probability. So conditional probability is, we are saying we drew the king on our second draw given that the first draw we drew an ace, right? So on the first card we pulled out, we got an ace. So since one probability is kind of depending on the probability of the other event, we say it's a conditional probability. So let's take a look at that before we get into our second multiplication rule here. So conditional probability, they are saying for an event B in relationship to an event A is the probability, okay, so is the probability that event B occurs after event A has already occurred. So of course we know the second event will happen after the first event has already happened, right? So for your notation for conditional probability, we actually use this little vertical bar. So we are saying the probability of event B occurring happens after event A has already occurred. So we put that little vertical bar in between B and A. So they are saying, and this is something you really got to be careful about, this notation does not mean that B is divided by A. It's not division here, guys. It just basically means that event B occurs after event event A has already occurred. Okay, so in the card example where we were talking about drawing a king on the second event and drawing the ace on the first event, we would basically say probability of king given that the probability of the ace or event ace had already happened. Okay. Okay, so just kind of putting this all together, your conditional probability is going to happen when you have dependent events. So your first event you will calculate like you normally do. So there would be no change in that. But when you calculate the probability for your second event, that's where the conditional probability is actually coming in, because your second event happens after the first event has already happened. And in this case, since we did not replace the card after we drew an ace back into the deck of our cards, so when we drew the king, the probability for the king ends up changing because we did not make that replacement. So since that card did not get replaced, we had dependent events. And for dependent events, even though you are multiplying these two probabilities, you will see our second probability is not just probability of B, it's probability of B given that event A has already occurred. Okay, so let's try and put this in a couple more examples so you can kind of wrap your head around this. So example 6 is talking about, for a specific year, 5.2% of US workers were unemployed. We are saying during that time, 33% of those who were unemployed received unemployment benefits. Okay? If a person is selected at random, find the probability that she or he received unemployment benefits if the person is unemployed. Okay, so let's see how we can do this. So they're asking us to find the probability that this person we select received unemployment benefits if the person is unemployed. So this is kind of the probability we're finding. They're receiving unemployed benefits and they are unemployed, right? So the probability of a person being unemployed is this 5.2%, right? So convert that into a decimal and you get 0.052. Now the second one is going to be the probability of people who were unemployed and received unemployment benefits, right? So B is for benefits, and we are saying they're receiving the benefits given that they are unemployed. So that was our 33%. So again, as a decimal, that becomes 0.033, and then multiplying those two numbers gives you 0.017, right? So again, that's a pretty small probability where we are saying a person who is unemployed and receiving unemployment benefits is only 0.017, or basically if you convert it to a percent, that would be approximately 1.7% chance that they would be unemployed and receive unemployment benefits, right? Alrighty, let's look at this next example. They're telling us, for example, 7, worldwide insurance company found that 53% of the residents of a city had homeowners insurance. So basically 50% of the people had homeowners insurance. We're using letter H for that group. Out of these clients, so out of these 53% people who already have homeowners insurance, 27% also had automobile insurance. So that's A. So the idea is if we select one of these residents at random, what is the probability that the resident has both homeowners and automobile insurance with this insurance company, right? So you're talking about having both homeowners and automobile insurance. So homeowners insurance would be the first event, and that's a probability of 53% or 0.53. And then for our second event, that's going to be people who already have homeowners insurance also have automobile insurance or auto insurance, and that would be a conditional probability, right? Because the condition is they have automobile given that they already have the homeowners insurance, and that of course they're telling us is 27% or 0.27. So when we multiply, you get 0.1431, and rounding it to 3 decimal places, you basically just get 0.143, right? So we're saying about a 14.3% probability that a resident will have both homeowners and auto insurance, right? So you can see again, not too bad as long as you understand the idea that these are dependent events and how that probability changes a little bit, okay? So they're talking about you can take the same multiplication rule and extend it to 3 or more events. So that's what this next example here is talking about. So they're saying 3 cards are drawn from an ordinary deck and not replaced. So the not replaced is the key part here, because that tells us when it says not replaced, you're looking at dependent events, right? Okay, so what's the probability that we would draw 3 jacks? So for 3 jacks, the first event that you start out with, there's going to be a total of 4 jacks out of your full deck of cards, which is 52 cards, right? But once we pull this one card out, we're not putting it back into our deck, which means you're only going to have 51 cards left in the deck total. And since we took one of the jacks out, you only have 1 jack left behind. So that's why you only have a numerator of 3 over there. So again, this is our second card that we're taking out, which means our deck is again going down by 1 number. So from 51, we are now down to only 50 cards in our deck. And again, since we kept the second card out, which means we will only have 2 jacks left behind in our deck. So that's your 2 out of 50 for that third card that you draw. So again, same thing, multiply all of them together. You end up getting 24 over 132,600. Reduce that fraction, 1 over 5,525. And again, as a decimal, round to the first non-zero number, and you get 0.0002, right? So this would basically be, doesn't matter what cards you are drawing, remember that total amount of your deck will keep going down, and then depending on what the cards are, the numerator will change based on that. Part B, we are looking at ace, king, and queen, right? So for ace, you would of course have 4 aces out of 52. But again, we're not replacing that card, which means you are now at 51 total cards. But now you're looking at king, right? So ace, we had 4. King, we will have 4. And queen, we will have 4 cards in our deck, right? So your numerator will stay 4 for the ace, the king, and the queen. But our denominator, because we're not replacing these cards, your denominator will still continue to go down. So in part A, since we were looking at all jacks, right? So if you took one jack out, you were left with 3. If you took the second jack out, you were left with 2. So that's why the numerator on part A kept decreasing. But in part B, because there are 3 different types of cards, right? An ace, a king, or a queen. So that's why your numerators will stay the 4, but then your denominator keeps going down by 1. And that ends up giving you, when you multiply, 64 over 132, 600, and then reducing that fraction gives you 8 over 16,575, or as a decimal, 0.0005. So again, really small probabilities, really small chances that these events can happen. Same thing on our part C. Here we're looking at the suits. So you've got club, spade, and heart, right? So there are a total of, hold on a second. There are a total of 13 clubs, 13 spade, and 13 hearts in our deck, right? But again, since we're not replacing, we start out with 13 out of 52 for the clubs, but we don't replace our cards. So that's 13 spades out of now 51 total cards, and then 13 hearts out of a total of 50 cards, right? So this comes out to be 2197 over 132, 600. Reducing that gives us 169 over 10,200, and that's a probability of 0.017. Okay, so again, pretty small. Now here, for part D, we are talking about taking 3 cards that belong to the suit of clubs, right? So if you're talking about 3 clubs, of course we start out with 13 total, with 52 in our deck. But since these will all be clubs, your numerator and denominator will both go down. So we took 1 club card out, so that left us with 12 out of 51 for the second one. This is the second clubs card that we're keeping out, so now you will only have 11 out of 50 for the third card as your probability. So when we multiply, we get 1,716 over, again, 32,600. Reducing that fraction gives you 11 over 850, or as a decimal, 0.013. So yeah, just kind of have to keep in mind what kind of probability you're looking at, what kind of cards you are looking at. And you can see in all 4 of these examples, we're trying to show how that can vary based on what kind of cards you're looking at. And then the last line there is saying you can use tree diagrams also to help you find these probabilities. So if it helps you to kind of visualize what you're looking at, you can definitely try to working with tree diagrams also. And I believe that might be something which may come in handy for this next example we're looking at, which is example 9. So let's see, we're talking about box 1 contains 2 red balls and 1 blue ball, right? So that's in box 1. Box 2 is going to have 3 blue and 1 red. Then they're saying a coin is tossed. If it falls heads up, box 1 is selected, and of course you draw a ball. If the coin falls tails up, then box 2 is selected and you draw a ball. So if using this idea, we want to know what's the probability of selecting a red ball. So we know there are red balls in both boxes, and then depending on which face, I guess, of the coin you get, you would be selecting your box based on that. Okay, so they are saying the first 2 branches here will designate either box 1 or box 2. So you can kind of see this right here. So that's And maybe you can see this better at your end, but this one here is probability for box 1. This one here is the probability, whoa, for box 2. So since there are only 2 boxes, right, you either select box 1 or you select box 2. So each of them will have a probability of 1/2 because that's 1 out of total of 2 boxes, right? Okay, and then they're saying from box 1, either a red or a blue ball can be selected. So this is us now going into box 1, and we are saying, let me go back here. There were 2 red and 1 blue. So that's a total of 3 balls, right? In box 1, again, let me go back here. There's 2 red, 1 blue. So box 1 has a total of 3 balls, and box 2 has 3 blue and 1 red. So box 2 has a total of 4 balls, right? Okay, so that's 2 red out of 3 total balls, so that's the probability of 2/3. There's 1 blue out of a total of 3 balls, so that's a probability of 1/3. For our second box, we have 1 red, so that's 1 out of a total of 4 balls, and then of course for B, it's going to be 3 blue balls out of a total of 4, right? So that's kind of how they're using the tree diagram here. So first we're talking about what's the probability you choose box 1 or box 2. So that's going to be 1/2 probability for box 1, 1/2 probability for box 2. And then from each box, this is where your conditional probability comes in, because that's red given that you choose box 1, or that's blue given that you choose box 1. This one here is the probability of red given you choose box 2. This one is probability of blue given that you choose box 2, right? And then when you calculate the probabilities, you're going to take the 1/2 for choosing the first box and then multiplying by the probability of choosing red balls from that box 1. So that's 2/3, which gives you a probability of 2/6, which I would probably go ahead and reduce it down to 1/3, but you can leave it for the same now. Same thing here from box 1. The probability of choosing box 1 is 1/2. The probability of choosing a blue ball from box 1 is 1/3. So that gives us a probability of 1/6. If you ended up choosing box 2, that's a probability of 1/2. You choose red balls from box 2, that's a probability of 1/4. So multiplying them gives us 1/8. For blue balls, probability of choosing box 2, probability of choosing blue balls from box 2, so that's 1/2 multiplied with 3/4, which gives you a probability of 3/8. So that's how you actually would calculate the probabilities for this little example here, and that's kind of what they're talking about here. So they're saying the first 2 branches designate, are you choosing box 1 or box 2? Then from box 1, are you choosing a red or a blue ball? And then same thing, if you chose box 2, then what's the probability of choosing a red or a blue ball? So that's what this tree diagram is helping us do. And then you can kind of go through this little paragraph here. It's kind of going over that explanation that I was just talking about. So I would say go ahead, read this little paragraph just to get an idea of what they're talking about. So just something I want to point out is, since we're using a coin toss to help us decide which box we are going to choose, that's also, you can kind of think of that also leads us to getting this probability of 1/2, right? Then they are, of course, getting into the details of how we came up with the probabilities for the red and blue balls. I've already talked to you about that. So they're doing this for both the boxes. Then they are saying you would multiply the probability of choosing the box with the probability of choosing the color of the ball. So this is where our final probabilities, which is right here on the extreme right, where they're showing you these little multiplications here. So they're talking about that in the second paragraph. So you can kind of look through that also. So like I said, read those two paragraphs. Now let's come back to our final question. So they're asking us, what's the probability that we end up selecting a red ball? Okay. So the probability of selecting a red ball either from box 1 or box 2, so that's the probability of red. And this is actually going to come from right here. So you can see the probability of selecting a red ball was 2/6 from box 1. And the probability of selecting a red ball from box 2 was 1/8. So this little guy here. So that's 2/6 and 1/8. So you're looking at 2/6 plus 1/8, which find a common denominator, which is 24. 8 plus 3 will give you 11 out of 24. Okay, and you will notice we are adding these two probabilities because basically they are mutually exclusive events here, right? Which is what we talked about in the last section. So they're using the addition rule here to come up with this probability, because there's actually no sequence of events happening here. Your sequence of events is choosing box 1, and then the dependent event would be choosing the red ball from box 1, or choosing box 2, and its dependent event would be choosing the red ball from the box 2. So that's why we were doing these little multiplication calculations here. So this is your multiplication rule 2 for finding the probabilities, but then here we ended up using addition rule 1 to come up with this total probability. Okay, so they're saying tree diagrams can be used for both independent and dependent events, and of course you can do this for sequences of events which are 3 or more. Okay, so just something to kind of think about. Alrighty, so that brings us to our discussion for conditional probability. So how do you find those conditional probabilities in the event it's not given to us, right? So you're actually rewriting your multiplication rule 2 formula to help us come up with the conditional probability formula. So this is your multiplication rule 2 formula where we take the probability of A and B, and that's equal to probability of A, which is our first event, multiplied by the conditional probability, which is event B, occurs given that event A has already occurred, right? So that's your conditional probability. So you'll see we're dividing both sides by probability of A. On the right hand side, probability of A cancels out with the probability of A on the denominator, and then you get conditional probability B given that A is going to equal probability of A and B divided by the probability of A, which is this formula right here. So remember, the second event happens given that the first event has already occurred, right? And basically this is how we come up with our little conditional probability formula. And then you've got your little cute Venn diagram over here. So that P, or probability of A and B, remember, is this common space between our two probability circles, right? So probability of A intersected with probability of B, and then little common area. So that's this numerator here, and then the entire probability of A is what you're putting on the denominator. Okay, and again, I would suggest reading this little paragraph here underneath your Venn diagram, which is kind of going over what I was just talking about. So yeah, I think I already talked about that. So yeah, just go ahead and read this paragraph here. So I want to look at our example 10 over here and look at how we can calculate these conditional probabilities. So we're back to looking at, and in this case, we're looking at colored chips. So you have a box that contains black and white chips. So they're saying a person selects 2 chips without replacement. So of course, without replacement, again tells us that we are looking at dependent events, right? So they're saying if the probability of selecting a black chip and a white chip is 15 out of 56. So this is that common area which I shaded right here, right, between both your events. So that's the probability. And then they're saying the probability of selecting just a black chip on the first draw is 3 out of 8. So this would be your first event, is drawing that black chip. So they want to know what's the probability of selecting a white chip on the second draw, given that on the first one you were selecting a black chip. So this is your conditional probability that they're asking. And you know, the easiest clue to know that they are asking you to find the conditional probability, you will always see this terminology, given that. So anytime they say this event happened, given that the second event happened first, that means you're talking about conditional probability. So even if you're finding conditional probability, or if you are finding the probability of A and B, and the conditional probability is given to you. So just look for that given that phrase, and you know which probability you're looking at, okay? So probability of black and white chip, which is this one here, they told us was 15 out of 56. And then the probability of selecting a black chip on the first draw, which is this, oops, sorry guys. There we go. Okay, so the probability of selecting a black chip on the first draw, which is this one here, they're telling us is 3 out of 8. So this is where, remember, we end up dividing to find the conditional probability. So that's 15 over 56 divided by 3/8. Keep the first fraction the same, invert the second fraction, and that changes division to multiplication. Go through that math, and it comes out to be 5 over 7, or as a decimal, 0.71. So this is your conditional probability when you are selecting on your second draw the white chip, given that you drew a black on the first draw, right? So 5/7 or 0.714. All right, let's see what this guy is talking about. Okay, so the probability that Sam parks in a no parking zone and gets a parking ticket is 0.06, right? So this is that intersection part between your two circles. And the probability that Sam cannot find a legal parking space and has to park in a no parking zone. So he has to park in a no parking zone is 0.20. Okay, so they're saying on Tuesday, Sam arrives at school and has to park in a no parking zone. What's the probability that he will get a parking ticket? Okay, so they're saying let N represent that he ends up parking in a no parking zone, and let T represent that he's basically getting a ticket. Okay, so the probability that he parks in a no parking zone and gets a ticket, they're telling us, is 0.06. The probability that he ends up parking in a no parking zone is 0.20, which is also given to us. So when you do that little division, you end up getting 0.30, which is the probability of getting a ticket when he ends up parking, or given that he's parking in a no parking zone. So that's your 0.30, or a 30% probability that he's going to get a ticket given that he parked in a no parking zone. So you can see how differently worded this example was here, because it's a conditional probability which is being implied in this question and in this statement right here. So you kind of have to read through that a little bit, okay? All right, so they're saying conditional probability of events occurring can also be computed when the data is given in a table form. And if you remember, we had talked about these table form examples in our last section also. And I think they're really useful because, again, you know, I'm a visual kind of person, so I like when I can see things visually. So that's why I like if you can draw tree diagrams. If drawing a table helps you out, then, you know, that may be something that you can try working through as you're looking through examples here. Okay, so let's take a look at this guy here. This is saying a survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. So here's the result of that survey. So looks like we basically, out of those total of 100 people, there were 50 men and 50 women, because you can see that's the total. And then 32 men said yes, 18 said no. So 32 plus 18 adds up to 50. And then 8 female said yes and 42 said no. And then if you add the columns, 32 plus 8 gave you 40. 18 plus 42 gave you 60. So just a breakdown of basically out of the 100, 40 people said yes and 60 people said no, right? All right, so you are looking at finding the probabilities that the respondent answered yes, given that the respondent was female, right? So this is your conditional probability. So they are saying, what's the probability that the person said yes, given that they were female? And for the second one, they're saying the respondent was male, given that they answered no. So this would be given that the respondent was male, given that they answered no. So these are the two conditional probabilities you're finding here. And then as you can see, we have defined M for male, F for female, Y for yes, and for no, right? Pretty standard. So our first one, we're trying to find, they said yes, given that they are female. So remember, using the rule for conditional probability, your numerator will be the probability that they are female and said yes, divided by the probability that they are female. Okay, so let's go back to our table. They are female and said yes for our numerator is going to be female and yes, which is 8 people right here, right? So that's going to be your probability of 8 out of a total of 100 people. And then probability that they are female, well, we know there are a total of 50 females. So that's going to be 50 out of 100. So when you put this together, you would have 8 out of 100 divided by 50 out of 100, which would honestly come out to be 8 out of 50, which would reduce down to 4 over 25, and then which would become 0.16. So there's only a 16% probability that they would said yes, given that they were females, which I think is kind of really low if you think about that. But that's the answer for part A. Okay. Part B was talking about what's the probability that they were male, given that they said no. So of course you have to find the probability that they said no and they were males. So they said no and they were males is this one right here. So that would be for both male and no, which is 18. So that's 18 over a total of 100 people. And then how many no's did we have? And that was a total of 60 no's, right? So that's the denominator, probability of no, and that's 60 out of 100. So again, this would essentially become 18 over 60, which can reduce down to 3/10 or 0.3. So we're saying there's a 30% probability that the respondent was male, given that they said no. Now here's something that might help you remember when you're working through these conditional probabilities. You see how this order is Y, given that it's F. So you can see F is the second value, so that's what's going on the denominator. So that can kind of help you remember which is the probability you divide by. Same thing here, you have m given n, so n is the second value, so again n is going to be your probability on the bottom, and then of course combination of yes and female. Oh lordy, I don't know why it's doing that. Okay, so then your numerators would be just a combination of female and yes, and then this would be probability of no and males on the second one. Okay, so that basically talks about our multiplication rule 1, multiplication rule 2, and basically multiplication rule 1 is for independent events. Multiplication rule 2 is for dependent events where you will have conditional probability. And so now we have also looked at how to calculate our conditional probabilities. Okay, so the last thing that we want to talk about is how can you find the probability of an event which we're saying at least this will happen. Okay, so let's take a look at this. They are saying multiplication rules can be used with complementary event rule. And we had, of course, looked at that, as you can see in section 4.1, to simplify solving probabilities of at least. So complementary events was, remember, if we said the probability of getting an ace from your deck of cards, if that was the main event, then basically the complementary event would be the probability that you're not getting an ace when you pick a card from your deck of cards, right? So we actually define this as the probability of at least selecting this one event to happening is going to be 1 minus the probability of that event not happening. So the probability of none. So this will be something you want to kind of use in this little part here, okay? So let's talk about how we can go about looking at these examples of finding at least one of these events happening. So example 13 here is talking about drawing cards where a person selects 3 cards from an ordinary deck of cards and they're replacing each card after it is drawn, right? So essentially you're looking at independent events here because you are replacing the card back into the deck. So they are asking us to find the probability that the person will get at least 1 heart. So that's your keyword right there, at least, right? At least 1 heart. All right. So we're talking about it's going to be easier to find the probability that the person will not select a heart in these 3 draws. And then basically you're looking at finding that probability of none. And then you can subtract it from the value of 1. So find the probability of not selecting a heart in those 3 draws and subtract it from 1. Okay, so basically they are saying to do the problem directly, you would have to find the probability of selecting 1 heart, 2 heart, 3 hearts, and then adding the result. So we are saying the event E itself, the main event, is going to be probability of drawing at least 1 heart. And its complementary event, E bar, is basically you're not drawing any hearts. So let's look at the probability of not drawing any hearts. So that's the probability of the complement. So basically remember there are 13 hearts in a deck of cards, right? Because that's your suit. So you are doing 52 minus 13, which is giving you the 39. So the probability that we do not draw a heart would be all the other cards except those 13, right? And since we are replacing the cards back in our deck, that's going to be 39 out of 52 for the first card. Because remember, you are drawing 3 cards from your deck. 39 out of 52 for the second card, and 39 out of 52 from the third card. You can reduce those fractions down when they come out to be 3/4, 3/4, and 3/4. Multiply them and you get 27 over 64. So this is the probability that we do not draw a card. And then to find the probability of the event itself, and actually there's a typo in your, because I just took this from your textbook, so this should actually be probability of E. hold on. So this should be the probability of E, and this guy is actually showing it as E bar over here. So this shouldn't be E bar, this should be E, okay? So this is where you're going to do 1 minus the probability of not drawing a heart. So that's 1 minus 27 over 64, which comes out to be 37 over 64, or basically 0.578, or approximately 57.8%. So they're saying a person will select at least one heart is going to be a probability of about 57.8%. Okay? So it actually does seem a lot easier to do it this way by using that idea of 1 minus the probability of none, which is what we're talking about here. And it will make your calculation go a lot faster. Okay, same thing's happening here. They're saying a single die is rolled 4 times. And what's the probability of getting at least 1 6? So those 4 times you roll the die, at least one of them should show us a 6. And this is what the probability we're trying to calculate, right? Okay, so let's talk about finding the probability that we get no 6s. So that's the complement of the event. And again, we'll subtract it from 1. So if you're rolling a die, the probability of getting a 6 is 1 out of 6, right? You have a total of 6 outcomes. One of them happens to be the number 6. So which means the probability of not getting a 6 will be 6 minus 1, right? So that's going to be 5 other possibilities out of a total of 6. So that's where they're getting this 5 over 6 from. But you'll notice they're raising it to the 4th power. So just think about it for a second. Why are we raising it to the 4th power? Okay, so the reason we're raising it to the 4th power is the same thing that we did here in the previous example. You can see how we took each probability of not drawing a heart, which was 39 over 52, or as a reduced fraction, it was 3 out of 4. So that 3 out of 4, or even the 39 out of 52, was being multiplied into itself 3 times, right? Which was the same thing as taking 3/4 and multiplying it 3 times by itself. And that's because we were drawing 3 cards. Whoa. We were drawing 3 cards from our deck, right? So that's where that number 3 is coming from. This number 4 is coming from rolling our single die 4 times. So that's why this is raised to the 4th power. So you're taking 5 over 6, the whole thing raised to the 4th power, which will end up giving you 625 over 1296. Subtract that from 1, and you get 671 over 1296, and that's a probability of 0.518, or approximately 51.8%, that you will get at least once. Come on, buddy. There we go. You are getting at least 1 6 when the die is rolled 4 times. So again, I hope this one makes sense, guys. And we are down to our last example. I know, finally. So this one is talking about the Neckwear Association of America reported that 3% of the ties sold in the United States are bow ties, right? 3%. So if 4 customers who purchased a tie are selected randomly, what's the probability that at least one of those people purchased a bow tie? Okay, so event E will be that at least one bow tie was purchased. Its complement will be that no bow ties were purchased, right? All right, so they're telling us 3% is the probability. Yeah, sorry, 3% was the probability that a bow tie was purchased, so that's the probability of E is 0.03, which means the complement that no bow ties were purchased, you would have to do 1 minus 0.03, which actually comes out to be 0.97, or 97%. do not purchase bow ties, right? They purchase the regular ones. Okay, so we are talking about selecting 4 customers randomly. So the idea that no bow ties were purchased is going to be your 0.97 multiplied into itself 4 times, or basically you could have, oh my lord, I'm telling you, this tablet is trying to drive me crazy. You can write this as 0.97 raised to the 4th power, which would end up giving you this answer right here, 0.885. So when you're trying to find the probability that at least one bow tie is purchased, that would be 1 minus 0.885. And that comes out to be a small probability of 0.115. So we're basically saying there's about an 11.5% chance that a person would purchase at least one bow tie. So pretty small probability, right? I guess bow ties are not that popular. So just something to kind of think about. So I've shown you 3 different examples here with our in our handout. So kind of look through those and see if you have any questions. And then what I would like to do next is, of course, look at some examples from our textbook so you can get a little bit more variety here. And then, of course, we'll look at more examples in class. Okay? All right, guys, so let's take a look at some examples here from our textbook. So we're starting out with example 4 over here. So you can say this one is saying the Gallup poll reported that 52% of Americans used a seat belt the last time they got into a car. So if 4 people are selected at random, find the probability that they all used a seat belt the last time they got into a car. So of course, the first thing you want to think about it are these independent or dependent events. And of course, if one person is wearing the seat belt and you randomly select another one, there's no reason that the first event will affect the second event, right? Or the first person wearing a seat belt will affect the second one. So since these are independent events, all you have to do is multiply the probability for each event and get your total answer. So here they're telling us the probability is 52% of the Americans used a seat belt, right? So what you're going to do here for this example, and hold on a second. Oh, come on. Sorry guys, my pen just stopped working, so I'm going to try and see if I can get it working again, okay? All right, there we go. So they're telling us that the probability, okay, apparently this guy is not wanting to cooperate with me today. So the probability that they wear a seatbelt or they wore a seatbelt last time, oops, is 52%. So as a decimal, that will of course end up becoming 0.52. And they're telling us what's the probability if we selected 4 people at random. So that's basically 4 people at random, which means you are multiplying this into itself 4 times, right? And remember what I said, since these events are not dependent, you're not going to have any conditional probability. So you can write it out like this. Or basically you can say, okay, the probability is 0.52. It's the same for all 4 people chosen at random. So that would approximately come out to be, rounding it to 3 decimal places, we are looking at 0.073, which would of course be approximately, if we convert this back into percents, approximately 7.3%. So I hope you can kind of see how these independent event probabilities work out to be. Okay, alrighty. Let's go back to our example here. The next one I wanted us to look at is number 26. Oh, sorry, number 6, which is if 25% of U.S. Federal prison inmates are not U.S. citizens, find the probability that 2 randomly selected federal prison inmates will not be U.S. citizens. Okay, so they're saying the probability is that 25% are not U.S. citizens. So if we select 2 at random, what will that probability be, right? So this guy here is example 6. So the probability that the inmates are not U.S. citizens. And that probability they're telling us is 25%. So that would of course come out to be 0.25. And so just like you saw in the previous example, since we're talking about choosing 2 inmates randomly, they are not going to be connected to each other, or basically they're not going to be dependent. So you can basically write this as 0.25 to the second power. And that one will of course come out to be 0.0625, and rounding that to 3 decimal places will become 0.063, or approximately 6.3%, right? So you can kind of see what that comes out to be. So pretty small probabilities for both examples that we looked at here. Alrighty. Okay, so the next example that we are looking at is going to be number 8. Okay, so number 8 here is talking about, it is reported that 72% of working women use computers at work. Okay, so 72% use computers at work. If we choose 5 women at random, this is the at least one example. So part A is saying find the probability that at least one doesn't use a computer at work. And part B is saying find the probability that all 5 use a computer in their jobs. Okay, so the first one is actually worded differently. They are saying find the probability that at least one does not use a computer at work. Okay, so the way we're actually going to work through this one, and this is example 8. So the probability that they are using a computer is given to us as 72%. In a decimal, that would be 0.72, which means when they are asking us to find the probability that at least one does not use a computer, you are actually going to do this as 1 minus the probability that they do use a computer. Okay, Okay, and so that's going to be 1 minus the probability of using a computer. But then remember, at the same time, they're telling us that we are choosing 5 of these working women at random. So because of that, we're going to raise this to the 5th power, and that will come out to be, let me see. Okay, so that comes out to be a pretty large number, so I will not go ahead and write that down, or should I? Well, I'll write it down for you guys. 0.193491763. Like I said, it comes out to be a pretty large number. Okay, so you would need to subtract that from 1, so that ended up giving us 0.8065, and it actually keeps going, so just round it to 3 decimal places, so that will come out to be 807 after the decimal. So that's a probability of approximately 80%. So that's a pretty high probability that at least one of them will not be using a computer. Okay, so this is our part A. I don't know why my computer is lagging a little right now. It was working fine before. Alright guys, part B is talking about the probability that all 5 use a computer in their job. So we have actually already calculated that as part of part A. Okay. So probability that they do use a computer. And obviously you can see that probability was the 0.72. And since we are talking about choosing 5 women at random, okay, why did this not come out? I apologize guys, I don't know what's going on. So that's this big large number that you had, 0.19349, and it keeps going. But let's round it to 3 decimal places, which will come out to be 0.193. So about a 19. Oh, this guy just does not want to work, does it? It's about a 19% probability. You are really driving me crazy here, computer. Okay, so that would be approximately 0.193, or as I said, a 19% probability that all 5 of them will be using a computer. So this was just an example of that. At least one I should actually include. This should say at least one does not use a computer, okay? Alrighty, there we go. So let's go back to our examples here. And the next one I wanted to look at was actually number 14, right over here. Alright guys, so number 14 here is talking about, in a scientific study there are 8 guinea pigs and 5 of them are pregnant. So we're saying if we select randomly, and here's the keyword, without replacement. So since they're saying without replacement, that means we're looking at dependent events. So they're saying if you select 3 at random without replacement, what's the probability that all of them will be pregnant? Okay, so remember there's a total of 8, and out of those 8, 5 are pregnant. So that's the probability that the guinea pigs are going to be pregnant. So remember again, this is going to be dependent events, which means for the first one, there's a total of 5 who are pregnant from 8. So we'll put that into consideration. And then since they're telling us this is without replacement, so let's say we took one of those guinea pigs out, which means now we are left with 4 that are pregnant, and that's from a total of 7, right? And again, we're going to keep this guinea pig out, which means now we are left with 3 pregnant guinea pigs, and that's going to be from a total of 6. So since this is without replacement, these are dependent events. So then when you multiply your numerator, that will come out to be 60. Multiply the denominator values, and that comes out to be 336. If you want to reduce the fraction, that will come out to be 5 out of 28. And then, of course, as a decimal, this guy will come out to be approximately 0.179. So you can kind of see that's a pretty small probability. And again, remember, they are telling us that we are choosing 3 of these guinea pigs at random. So that's why we are doing this for 3 events, right? So 0.179 is what you're going to end up getting for this. So this was an example, again, looking at dependent events. And then let's see, the next example I have chosen for us to work through is, if I can find it, number 32. So let's look at that. And this one is using a table to help us out. So in this case, the first thing we're actually going to want to do, oh sorry, this is 32 right here. Of course, you're going to want to add all your rows and columns. So in this case, let's see, we are saying below are listed the number of doctors in various specialties by gender. So we've got male, female, and then the specialties are pathology, pediatrics, and psychiatry. So if we choose one doctor at random, what's the probability that it will be a male doctor given that they are a pediatrician? For part B, they are saying what's the probability that it's a pathologist given that they are female? And then they want to know for part C, are the characteristics female and pathologist independent? And then we want to explain our answer. So let's take a look at how we can go about doing this example here. All right, guys, as you can see, I was just copying that table over here so we can go ahead and take a look at these. So the first thing we're going to want to do is add up all our columns and our rows. So let's start with pathology. That will end up adding to a total of 18,179. Then add up your pediatrics column. So this one adds up to 66,371. And then the psychiatry will add up to 40,095 doctors. Okay, then let's add up our total number of male doctors, which comes out to be 73,398, and add up our total number of female doctors, which is 51,247, and our grand total, either add the male and female total, or you can add the different specialties, doesn't matter. Your grand total from both ends should come out to be 124,645 doctors, right? Okay. Then for part A, they were asking us to find the probability that it's a male given that they are a pediatrician, right? So the way, because you're calculating your conditional probability here, right? So remember, if you go back to your handout and look at the formula for conditional probability, this will come out to be taking the probability where the doctor is a pediatrician and a male, and then dividing this by the probability that they are a pediatrician. So let me see if I can keep this on the same page. So this would be pediatrics and being a male. So that's going to be this number right here, 33,020. And remember, that's going to be over your grand total of 124,645. And then we are dividing this by the total number of pediatric doctors. So that's going to be this number here. So that is 66,371, again over the grand total of 124,645. So basically it comes out to be 33,020 over 66,371. And then if you just do a decimal approximation, this should come out to be approximately 0.498. So just shy of being 50%, right? So we're saying out of these total doctors that were listed, about 50% are going to be male, given that they are in pediatrics, right? So that's how this first probability comes out to be. Then your second one was finding the probability for a pathologist, given that they are female. So that's our part B, probability of being a pathologist, given that they are female. So this one, of course, would, using our conditional probability formula, would be they are both female and pathologist, divided by the probability of being a female. So female and pathologist would be this number right here, 5,604. Again, out of our grand total of 124,645, and then you're dividing it by the total number of female doctors, so that's a total number of 51,247. So 51,247 again out of our grand total. So this fraction basically will come out to be 5,604 divided by 51,247. And as a decimal approximation, this comes out to be 0.109. So about approximately, I guess you can say 11%. So 11% of the doctors would be pathologists, given that they are females. Now here's the C part. And let me show you that question one more time. So they are saying, are the characteristics female and pathologist independent? So even if you just look at the table, you can see, and we just did this in part B also, that female and pathology have this overlap, right? So you have female doctors who are also in pathology, so that actually tells you that these will not be independent events. So you can just basically say something like this, that the probability of being a pathologist, given that they are female, is obviously not equal to the probability that if you just look at all the pathology doctors, because you would definitely have an overlap in this case. So we would say no, they are not independent. So this would be for part C. This was our answer for part B, and then this was our answer for part A. So this was example number 32 from your textbook. And then I think I had maybe one more example that I wanted us to look at. Yes, I did. Okay, and this one is going to be number 48. Okay, 48 here. So this one is talking about selecting a letter of the alphabet. So we're selecting 3 letters of the alphabet at random, and we want to know what's the probability of getting at least one letter to be an X. And they're saying letters can be used more than once. So when they say letters can be used more than once, they're basically talking about independent events. So if you've used the letter once, you can use it again, right? Kind of like you're replacing the letter back into your alphabet. So we need to find that probability, and then they are saying, would you consider this event as likely to happen? And then of course give an explanation of why do you say that. So let's take a look at number 48 over here. Okay, so the first you have to think about, they're talking about what's the probability that we will get an X as our letter, right? So out of a total of 26 letters, we know one of them is an X. So that's a probability of getting 1 out of 26. Now this is one of those at least one questions, which means we also want to talk about what is the probability that the letter is not an X, right? So that of course means if one letter is X, that means the other 25 are not an X, right? So that means that's going to have a probability of 25 out of 26. Now they are saying we are choosing, and this is at least one of the letters is an X. And since we are choosing 3 letters at random, your probability, you're going to end up writing it this way: 1 minus the probability of not being an X, which is 25 out of 26, and you're going to raise this to the 3rd power because of those 3 letters that we are selecting at random. And so this calculation, if you go through that, actually comes out to be, and let me see, I got this right. Okay, so this comes out to be 1951, or 1951 over 17,576. If you write this as a decimal, which is probably what we want to write it as, comes out to be, in a rounded answer, 0.111, or approximately 11% if you want to think about it in percents. So that's a pretty slim probability, right? Because you are only getting a probability of, like I said, approximately 11%. So we would say, because you know the second question they were asking us, would you consider this event likely to happen? For it to be likely to happen, you know, it has to be more than 50%, and we are nowhere near that. So we would say the event, is unlikely to happen, or unlikely to occur since our probability is only about 11%. Okay. So, like I said, if you are between 0 and 50%, we usually say the events are unlikely to happen. If you are between 50 to 100%, we say the event is likely to happen. Right at 0%, we say the event is impossible to occur. At 1 or 100%, we say it's certain to occur. And then, of course, if you are right at 50%, then we say there's a 50-50 chance that that event will happen. Okay, so this was problem number 48 that I wanted us to look at, and then I'll have a few different examples that I'd like for us to do in class, so that way you get just a little bit more practice, when we are going through these examples. All right, guys, so look through this lecture, and of course let me know if you have any questions. So this was section 4.3 that we just got done discussing. All right, guys, have a wonderful day, and I will see you in class.